Welcome everybody. Good afternoon, everybody, and to this EURASIP seminar. This is a brand new initiative by EURASIP, and the idea is that there'll be a series of webinars organized by EURASIP, or more specifically by the technical area committees. And the one we have here today is organized by the EURASIP ASMSP TAC, which I am the chairman. And I'm very pleased that today here, the webinar will be given by Efren Fernandez-Grande from the Technical University of Denmark. And his talk is entitled Sound Field Analysis and Reconstruction, Recent Developments, Challenges, and Outlook. So please go ahead, Efren.
Yes, thank you very much, Mads, for the introduction and for the invitation to present here. I'm very glad. I'm very glad to participate and to share some of the work that we've been doing the last years. I hope that you can all hear me well and that you can see the full screen of the presentation. So so as I said, I'll be talking about the sound field analysis and sound field reconstruction. So essentially measurement techniques and signal processing for reconstructing sound fields in space and time. So perhaps to begin with, we could start by just reflecting on acoustic sensing, and in fact how fortunate we are that acoustic and audio instrumentation has improved so much since the mid 20th century or so. So transducers continue, getting better, cheaper, some of them smaller, and in a way that we can take for granted the measurement of acoustic signals. Now, one thing when you look at the essence of acoustic sensing, one thing is that it is fundamentally measuring sound pressure variations at a position in space and as a function of time. So basically, it is a temporal measurement in general, right? So what happens when we want to measure sound across space, when we're interested in spatial properties of sound? So there's also been great advances over the last few decades with the advent of array technology, microphone array technology. So starting, for instance, with intensity probes being, well, just a finite difference approximation, sound field probes and 3D intensity probes, microphone arrays in different configurations, either baffled on spheres or planar and so on. Now, this, if you notice, most of this measurement instrumentation is concerned with measuring at a local area of space. And there is one fundamental challenge, as much as this has advanced and continues to advance, there is one fundamental challenge that we cannot really get rid of, that it's very much in the nature of sound. And it is that, as you will surely are aware of, is that the audible wavelengths of sound in air, and audible by humans, I mean, span orders of magnitude from 17 meters length to 17 millimeters length. So we're talking about wavelengths that are larger than some buildings, and then as small as something like that. So this poses just a fundamental challenge. As I said, we cannot get rid of that because it's very much the nature of sound. And essentially what happens is that at low frequencies, we cannot measure over apertures that are sufficiently large enough, and that at high frequencies we would need such a small spatial sampling distance that we cannot afford the number of sampling points in space, which means that we just have to deal with an inherent band limitation in both ends of the audible frequency range. So based or taking from that, just as illustrate what we're talking about, is when we're concerned about sound fields in, for instance, rooms or outdoors or any three-dimensional space, we are also facing a three-dimensional sampling problem. So the number of measurements also increases with the power of 3. So essentially, we just have a too large demand for spatial sampling. To illustrate this, let's consider just 1 cubic meter, 1 cubic meter volume. It would require, if we want just to sample up to 5 kilohertz and we just have uniform sampling and satisfying Nyquist, we would require almost 30,000 measurements for just such a relatively small volume of space. And if we wanted to take the full audible range, then we would be talking about almost 2 million measurements. So it is clear that we cannot go about it just directly brute force adding more measurement. Like it is just too expensive, right? So I guess a central question is how to effectively address this problem, and this is what the talk is mostly about. Before I go to the things that I will discuss, just a bit of motivation of why is this relevant? What's the motivation behind wanting to do this? So first relevant application you could say is audio, spatial audio and reproduction, also virtual and augmented reality, as well as navigable reproduction of sound. So basically where a listener is immersed in a sound field and can move about it and virtually experience an audio signal that's corresponding to the position within the sound field, right? We could also think of sound field control, where knowing how sound is on over a spatial aperture enables us to introduce additional sources and manipulate the sound field. In the example that I show here, it's adding an array here of secondary sources to cancel the sound field at these 2 positions, or actually minimize the sound field. Other applications are analysis and visualization of sound. So if you have a complex sound fields as the example here, in the process of absorption in a reverberation chamber, basically being able to visualize and understand complex processes. And also, let's say, architectural design, preservation of historical spaces, and so on, where there is a value in just mapping what the sound field is over these halls of historical significance. And in general, we could say that this is relevant for any area that's concerned with one or other spatial property of sound and a sound field. Okay, so there's plenty of areas where this is relevant. Now let's get back to the question: can we actually measure sound over large spatial apertures? And here I will talk about 3 say research directions that we followed here in the group. The first one is looking into sensing methods and actually trying to examine sensing principles that are inherently spatial, mostly focusing on the acoustic interaction. I will explain that just in a moment. Afterwards, another track that we follow is trying to provide informative physical models that enables us to, from a few measurements, interpolate and extrapolate to reconstruct the sound field. And lastly, also data-driven and machine learning models to, for example, extend the bandwidth artificially, or try to obtain an enhanced reconstruction and predictions. So that's kind of the 3 directions that I will touch upon today. So the first one, sensing, it's about acousto-optic sensing. And I imagine that some of you are familiar with this, some other maybe not. So let me start by explaining what this is about. So the acousto-optic effect is a phenomenon that describes the interaction between sound and light. Essentially, it's the phenomenon by which light is refracted and experiences a retardation effect, so variable light speeds, as it traverses a sound field. What happens if we see, for instance, imagine this red line is a beam of light. Light will travel somewhat slower here where there's a high density of particles, and a bit faster here, right? So depending on the density changes in the medium, in our case, that's air. So depending on density changes in air that are due to sound, then light will travel faster or slower. So we can actually sense this in different ways. One of them is using optical interferometry. And here what we are doing is sensing a variation in the phase of light that, if you see, depends on the acoustic pressure. So you notice there is a line integral here over the sound pressure, and this line represents the travel path of light. So graphically, imagine we have a laser and we emit a laser beam that traverses this object, which is a sound field. So the gray area here is a sound field, and then it reflects off a rigid surface. That's actually important because in order to measure this acoustic pressure, we don't want to measure the vibrations of this surface. So pointing at a rigid surface, then it's reflected, collected again by the laser, demodulated with this reference beam, and then this actually gives us a quantity that it's proportional to the line integral of this pressure. And I'm sure that some of you are already anticipating that, okay, here you're measuring one projection. So if you want to recover this sound field, you would need multiple projections in order to obtain a tomographic image of the sound field, right? So through obtaining multiple projections, one could obtain or reconstruct tomographically the object, in this case, a pressure field in space. Now, the issue with tomographic techniques, conventional tomographic techniques, is that they are not very well suited to acoustics, essentially because they require a too high number of measurements that we don't have, and also they often require restrictive scanning configurations, say parallel beams rotated at equal angular intervals and so on, right? So when we started looking into this, we realized that we had to come up with some other reconstruction method that would be suited to sound. So what we did was actually to include the elementary waves, so in this case plane waves, as an interpolating basis for the measurement. So as here are the projected measurements, so its line, and then if you notice, this is a plane wave superposition where the basis functions are integrated over the path of the light. So essentially we have these measurements and known coefficients, so that we can obtain these coefficients by a regularized inversion. In this case, we solve it using lasso sparse regularization. Then once you know these coefficients, then you can obtain the pressure field like that. So what this actually enables to do is to, first, one can use less measurements because of using an interpolating basis that satisfies the wave equation. And also it enables us to measure arbitrary projections so that we can measure the sound field in situ. We don't need necessarily parallel beams and so on. So let's actually look at how this works. And of course, before going into the experiment, remark, and I'm sure that you are seeing this, that here we're not measuring the sound field at a point, but we are just measuring the sound field over space. So it's inherently a spatial sensing method. So here we have a test in our anechoic chamber at DTU, where we have a loudspeaker on one side. This is a laser Doppler scanner vibrometer. So basically it has some moving mirrors, so the laser can move about. And we are measuring or projecting the laser onto this rigid beam, right? So seen from the top, we have the loudspeaker, the laser beam at this rigid surface, and then we are measuring over this projection. The dashed line represents the area in which we will attempt to reconstruct the sound field. So notice that there is some interpolation as well as extrapolation of data. So if we were to use standard conventional techniques, as for example the use in CT scanning, the type of reconstruction we would obtain is something like this. This is a widely used method, the algebraic reconstruction technique, where basically each point in space is just taken as a pixel, so there is no interpolation basis. Now, again, because we know that we are measuring a sound field, it makes sense to use some wave interpolation. So when we do that, what we obtain is something like this, where you clearly notice the reconstruction of the wave field, the curvature corresponding to the position of the source, and you see that there is particularly greater accuracy within the measurement area, but also outside the measurement area, there is a sensible, let's say, reconstruction of that wave field. But well, this is a simple case, so let's look at something a little bit more interesting, which is a measurement we did in one of the rooms in the lab. Here we want to reconstruct the sound field in a volume, so we measure with the same laser. We measure over this sort of pyramid shape onto a rigid wall, and we want to reconstruct the sound field in this volume. Notice that we also have here a conventional measurement microphone, and that's just to check later to assess the quantitative accuracy of the measurement. So basically to compare with it. And we want to reconstruct the sound field here. So here is some snapshots of the process, but let's probably more illustrative to look at this video. On the left, we have the reconstructed sound field in the volume. On the right, we have a simulation done with using simply an image source method to keep track of which reflections is it that we are seeing. So what we notice, let me see if I get the video to start. Yes, there we go. So you see first the direct field that it's arriving from that side, and then trailing just after it, it's the wall reflection behind. Then we see the reflection from the ground, now interfering with the opposing wall, and then a second order reflection from here, from the ground, and so on, and also interference. So we see that we are actually observing the sound field that we expect in that volume. And I will, while I talk, I'll just play it again. So to me, the significance of this is that it is after all, a remote sensing principle. So we are not immersing a transducer in the area that we are measuring, but we are able to actually capture all these pressure variations remotely. Now, it's true that we do have a fairly large laser head, so there is how to say, a bulky piece of equipment, but it is not introduced within the reconstruction area, but externally. Looking at the quantitative accuracy, there is a fairly good accuracy. I think that some of these variations that we see have to do more with slight position mismatch of the microphone and the reconstruction point, but it is fairly okay. And another thing, let me just go back. Another thing to consider is that with this we have measured the sound pressure, but because we know the sound pressure in space, we also know what's the spatial gradients of it, so it's easy to estimate what is the particle velocity and sound intensity of the field. So we not only have access to what are the pressure variations in space, but also how air is moving, so both potential kinetic energy, and therefore we have a complete characterization of the sound field. This enables us to look at the intensity. So, for example, here this is a side cross section of the sound field. You notice that the source is around here, and there's all these circulatory patterns that are characteristic of wave interference. And we have both time average as well as instantaneous intensity. All right, and finally, before we switch on to the next topic, another thing that we examined related to this is the reconstruction of sound fields at high frequencies. And there is an issue that some of you might have encountered, which is if you have a sensor array at high frequencies, you know that you do need a fairly short, small spacing between transducers. So eventually you end up with a very dense array. in order to measure small wavelengths, right? But then this dense array also becomes very invasive because it introduces a lot of scattering and so on. So we thought that actually a potential benefit of using this non-invasive principle is actually to be able to measure at high frequencies over very dense or well over at high frequencies with very dense measurements in order not to disturb the sound field. So this is what we did here, where we have a vibrating plate and we're measuring again onto this rigid bar, and then we're able to reconstruct the sound field at several kilohertz. Here on the right, you see intensity flows that are generated by the plate and then being reabsorbed and circulating around it and so on. But yeah, I won't enter into more detail of this topic, but I'm happy to elaborate on it on questions. Yeah, so the next thing that I wanted to talk about is physical models for volumetric sound field reconstruction. So here, as I mentioned earlier, the paradigm that we are seeking, or actually the objective, is given a sparse or incomplete set of measurements of the sound field, can we actually reconstruct, say, interpolate and extrapolate the sound field accurately? And for that, one could use standard reconstruction techniques. But we did that too, but also what we've been working on lately is trying to develop informative models to actually seek what are generalizable properties of its sound field, and then find informative models that can actually provide a better reconstruction. To give an example, I will talk about rooms and sound fields outdoors. In the case of sound fields in rooms, there are some very marked properties that are shared across rooms, regardless of size and so on. So first, we know that sound field will tend to decay exponentially, maybe a single or multiple decays. We also know that reflection density, or the density of reflections, will grow with time squared. And we expect that there's going to be a direct sound, some early reflections, and then late reverberation with less energy and more growing density of reflections. And this is true for virtually any room or enclosure you are in. Of course, you may find some exceptions, but that's pretty much a highly generalizable structure. So we looked into several models. One of them that I talk about here is implementing this structure in the model, where we have a direct sound that's modeled by a cluster of point sources. Notice here, this is in time domain. So we are actually using a cluster in case that the source has directivity to be able to model that directivity to some extent, followed by some other point sources that model early reflections at a finite distance, and then the late part of the reverberation modeled as a superposition of plane waves, as a dense superposition of plane waves that have a much more chaotic structure. And then we solve this probabilistically as a Gaussian process. For instance, here in the late part, we used a Bessel kernel, isotropic Bessel kernel. And in one case, solved using stochastic variational inference, so basically to obtain the whole distribution. And then in another, solved using just a point estimate to obtain the map using kernel regression. All right, but essentially the idea is that in the case of sound fields in enclosures, find what is a marked generalizable structure that can be employed to obtain better predictions. So we have an experiment here in one of the rooms, one of the lecture halls or lecture rooms at DTU. It's a relatively small room. You have the volume there, reverberation time about half a second. And what we did here was with this robotic scanning arm, so we could program it to measure sequentially. And then we measured a spherical array here with roughly 48 microphones at the center of the wall, and then at the center of the room, or midway in the room, and then a line here of microphone positions to use as reference, as true data basically to validate if from the measurements obtained or from the measurements with the spherical array, we could predict what the pressure was further away with the array. I hope that the setting is clear. The source, we have two sources for this experiment. I will use this source here. In another experiment, I will use a further source, you will see. But anyways, this is the true field. So this is the line of measurements that we measured with the robot across the width of the room. So in that diagram is this line that you have there. What we see, also notice that this is space and time, right? So we have space, that's a line, and then time by when waves are arriving. And we find first the direct sound, followed by the ground reflection. Soon after the ceiling reflection, you notice that it's slightly attenuated because there are absorbing panels on the ceiling, then some lateral reflections, back wall, and so on. So we find the wavefronts that we would expect. If we were to reconstruct this using just a plane wave, a conventional plane wave expansion, using sparse regularization, the type of reconstruction we would obtain is this one, right? And by the way, I didn't say this, but these dotted lines show the area in which we have measurement. So that's basically the diameter of the spherical array. So what we see here is that inside the measurement area, so the interpolated points, the reconstruction is in fact not bad at all. So you have, again, direct sound, floor reflection, ceiling. Here you have the back wall, lateral reflections, and so on. But then when you extrapolate it, basically, there's the model cannot predict what's happening because what we are observing in the room are not plane waves, right? If we would use just some other method here, we looked at simply a Bessel isotropic kernel. It actually will tend to extrapolate. So indeed, inside the measurement area, it does a fair job, but then outside it just predicts highly reverberant or reverberant isotropic arrival. So that's not correct. And then with a method that actually encodes the structure that we find, so that's the one that I presented earlier, what we find is that both within the measurement area and especially the extrapolation, the reconstruction is fairly good. Notice that especially direct sound and these early arrivals are well modeled. You notice that here in the back wall, we start having some model discrepancies. So the point sources that we used in the model do not agree with the spherical or the divergence of the true sound field. So therefore, in order to have a more planar wavefront here, we have to activate multiple point sources in the model, and then it diverges as we go further away from it, right? And then the later part where we used basically a random plane wave field of superposition of plane waves, then it's also relatively good. I mean, of course, it doesn't recover these strong wavefronts like that, but it does an okay job. Okay, one thing to highlight is the fact that we are from a measurement that's about 50 centimeter, half a meter in diameter. We are reconstructing over an aperture that's almost 5 meters. So there is a huge extrapolation distance. Some other experiments in maybe a more relevant auditorium than the one we have here. This is in the Niels Bohr Institute. So this is actually the lecture hall where Niels Bohr used to host the Copenhagen physics conference. And we have here the likes of Paul Dirac, Heisenberg, Brillouin, etc. So it was, very important for the history of science, let's say. So we were earlier this summer doing some measurements there. We brought in the robot, this robotic arm, and an eigenmic. So you see here we were measuring with the robot along the width of the room, also line array for reference. And then with the eigenmic, we thought of having just a distributed array. So we measured at these 3 positions in the room. And essentially the problem that we are proposing is from these 3 measurements, 3 distributed array measurements, can we actually reconstruct the sound field over this line and therefore over actually most of the volume of the room. And then what we obtain is something like this. This one, as I said, is actually not solved through the entire variational inference, but just as a kernel regression, so obtaining only the map. And what we have, well, if we look first at the true sound field, it's a bit more complex. I'll just go back one slide to show you one thing. Here, the source is placed on this wall, so basically the waves are traveling through the entire room. And notice that one wall is straight, the other has a few windows there. So what we see here, we look at the true field, is a direct field, and there is far more scattering because of all the benches that you have in the room. You see the reflections from this wall here, that there's windows, there's a slight discontinuity or diffraction from the windows, whereas the other wall provide or give rise to these clear wavefronts like that. And when we look at the reconstructed field, you see that it is fairly similar. There's some proving and noise here that was not suppressed, and then you see that it does a pretty good job at identifying most of the reflections, especially towards the late part. You see that some reflections, or the later part, some reflections are slightly overestimated, many of the others are sort of lost, but it actually gives a quite good picture. If you look at the here, the room being able to reconstruct over the entire width, and if we would look at the volume of this or this diameter and the volume that it would lead to, pretty much we're reconstructing the sound field over most of the volume of the room. So we were quite happy with these results. Now, one quick remark to bring up here was also sound field control outdoors. So we've been talking about rooms, but there's other environments where you can find quite how to say, the generalizable properties. In the case of outdoors, typically there will be a ground reflection and then some atmospheric propagation conditions that can be accounted for. So we use that in a project that was concerned with controlling the sound radiated by concerts outside the concert area, and here by using a few sample points we could estimate what the sound field would be over these spatial apertures, and introducing an array of control loudspeakers we would actually emit an anti sound field or a canceling sound field to actually decrease the sound pressure at those points. Okay, and so we've covered so far something on the sensing principles for sound field reconstruction, also physical models to improve the reconstruction, and the last thing I planned to talk about was machine learning models to address this problem. We did some other things like dictionary learning for obtaining reverberant functions and so on. I will talk about two things here. One is the use of generative models and generative adversarial networks to try to extend the bandwidth of the reconstruction. So early in the talk, we reflected on the fact that the spatial sampling problem in audio is inherently band limited because of the orders of magnitude of audible wavelengths. So given that band limitation, can we actually extend the bandwidth artificially using generative models instead of increasing measurements, right? So that's the one question that we addressed. And then the other that I will talk about is with the advent of physics-informed neural networks, can we actually obtain better predictions by ensuring that the predicted quantities fulfill the wave equation, right? So that's the two things we will talk about. So regarding generative models, again, I'm sure that most of you are familiar with them, but it's essentially having, say, two competing networks, a generator discriminator, and they compete, one generating fake data and the other trying to distinguish between real and fake data, up to the point where then the generated data is plausible or realistic enough as to fool the discriminator, right? So here we did this with the notion of, well, if you have corrupted. We looked at impulse responses, not directly audio audio sequences, but say if you have impulse responses that are corrupted and band limited, can we actually train a generative network to enhance them or to reconstruct them in a way that they appear to be full band, right? And we looked at 3 state-of-the-art models here: a compressive sensing generative model, a conditional GAN, and hi-fi GAN by these three studies, and looked at the performance in the context of room impulse response reconstruction. So here we have a test in one of our listening rooms. We have a spherical array of microphones, and this aperture that you are seeing here is a circular plane that we use as reference data to assess the performance of the methods, right? So essentially from this array, measurement array, then we predict the room impulse response, and then we try to actually see if the generative models can actually improve the reconstruction. Here it's shown in terms of as a frequency response to see actually that bandwidth extension. The dashed line indicates the sampling limit. So above it, beyond it, everything should be undersampled. And then we have just the conventional plane of reconstruction and the 3 models. And you see that, you know, some of the models don't do that well, some other do better. In particular, this hi-fi GAN performs quite well. And one thing to remark, or that we found quite revealing, is that when looking at the error of the phase, pretty much all of them, and particularly at high frequencies, all of them were wrong, right? And in fact, the generative networks, the generative models, they are actually synthesizing fake data, plausible, but it is fake after all. So the phase was never better than the conventional reconstruction, and then some of them did actually improve in terms of magnitude. So so in that sense, we were hoping that, at least in terms of also subjective plausibility, we could extend the bandwidth of the reconstruction without additional measurements. Now, the main other work that I wanted to talk about in this area is physics-informed neural networks, which I imagine you're also familiar with. But the aspects that are most attractive is that in this case, the predictions of the model are guided by physical principles. So in fact, we ensure that the predictions fulfill the wave equation, and also they require few training data, right? So by the way, I didn't say, but in the previous model, so we trained one of them with experimental data, and the 2 other with synthesized random wave data. Yeah, so here what we have is this physics-informed neural network, as was proposed in the work of Wang in 2020. And what we have is a data fitting term, and then here the predictions are subject to fulfilling the wave equation, essentially. So we have here a modified multi-layer perceptron, and then what we have is 2 shallow encoders with 2-layer seeds, and then here the features that go to the MLP to obtain the predicted pressure. Important on this case was the use of sinusoidal activation functions. So we will look at another test that we performed also here in the lab. This was an initial test where we measured over shown here in the diagram too. So we have a measurement over this square of 30 by 30 microphone position. So that's relatively dense, but that's also to have a reference for quantitative comparison. And then we have a training set of 10 by 10 microphone positions. So essentially we have a grid of 10 by 10 that we use for training the network. And then once that it is trained, we predict the sound pressure at these 30 by 30 positions. So here is the true data measured on 30 by 30, and this is the measurements used for training, so the 100 measurements. You see actually that the sampling, or when you look at the measured data, it is relatively undersample, or one could imagine that it's hard to reconstruct full bandwidth. And you see, using just the conventional plane wave expansion, you can see that there's all sort of artifacts, aliasing and Gibbs and so on, right? So it's even hard to distinguish the direct field. And then when looking at the prediction provided by the pin, it is not perfect, but it is actually much better. In particular, the direct field is quite well reconstructed, this ground reflection. Then the lateral reflection is a bit less, but it is a quite good performance. And yet one other very important thing here is that we are not just predicting sound pressure. Sometimes when thinking of sound field reconstruction, one thinks of, say, analogous problems such as in painting, right, where you have some data and you want to fill in the missing gaps. But here it is in fact quite different, because we are actually looking at a physical quantity, and therefore, although we are measuring pressure, but we also want to have access to characterizing velocity and sound intensity. So basically the other field quantities, to have a complete characterization of the process. So so this is what we show here, where by auto differentiation of the network, then we have a direct access to the gradient of the predicted quantity, the sound pressure, and therefore we can also calculate particle velocity and intensity. And here you have different snapshots of here the direct field in terms of velocity and sound intensity, clearly representing the wavefront. And in this somewhat later, when there's multiple interfering waves, we see again meaningful velocity, so movement of air, as well as flow of energy corresponding to that interference. Now, one thing, by the way, about the importance of obtaining sound intensity, or having access to sound intensity information, is the fact that many processes are described in terms of energy, are fundamentally energetic processes, such as sound absorption, transmission through partitions, or when we think of diffusion, that it's highly relevant for parametric audio reproduction and so on. These are very much described in terms of sound intensity. So it is highly relevant to also model that. And this is ongoing work. It will appear next month in JAS, and we have also some ongoing collaboration with Politecnico in Milano in similar things. So it's, yeah, we were enjoying quite much this work. And here we have some data from the Royal Theatre in Copenhagen. That was a very fun measurement campaign, also with quite a bit of pressure, because they have shows every night, so we had to work very quick. But yeah, we measured with the robot here this also aperture of 16 times 16 positions, and then used a training set of 8 by 8 positions to reconstruct over that aperture. And here, notice the sound source is far on the stage, and we are centered slightly to the left in the balcony of the hall. And here is where the Danish royal family sits. So yeah, so let's see. There's this video here showing the ground truth measurements and the pin reconstruction. That's a direct field. It's very planar because the source is far. Then there's, if you notice, a slight reflection from the back wall and a lot of scattered components from furniture and seats. You see there are lateral reflections and so on. So this is I think for the analysis of concert halls, it's I believe quite valuable information. You noticed here a strong reflection also appearing there. So and once again, in this case, for instance, when considering also diffusion in concert halls and so on, having access to the instantaneous intensity is quite valuable. You notice that clear wavefront appearing here, a lot of more scattered chaotic components, and later appearing some of the sidewalls and so on. So you are actually able to also observe how acoustic energy is flowing on that area. Okay, so yeah, and that's the other reflection I was talking about earlier. So yeah, we're wrapping up. I have just a couple of minutes left, so I'll wrap up. In conclusion, we have been working on enabling spatial measurement of sound over large apertures and exploring a few different directions, both novel sensing methods that are inherently spatial, and we talked about the acoustic effect, also informative physical models to try to extrapolate as much as possible for navigable audio reproduction, etc., as well as machine learning models to try to exploit the information that we already have measured and try to enhance that data. In terms of outlook, I think that indeed when we look at the field and there is considering AR, VR, and this whole these whole advances in navigable sound, I think that having access to remote sensing is important also for control of sound. So if you don't need to have reference sensors in the medium, but you can actually sense that remotely, that would be a huge advance. And also having indeed more informative models as well as machine learning models for improving and enhancing the reconstruction and our ability to measure sound in space. So with that, I would like, well, that's the references of the studies that I touched upon today, and I would like to acknowledge my team. So Samuel has done a lot of work on acousto-optics and some of the other things, and Efren and Antonio, as well as Manuel and Diego, who are no longer in the group, and collaborators Peter Gerstoff and Earl Williams that participate in several of the studies. So funded by Willum Fonden, which I'm grateful to as well for money with no strings attached. And yeah, thank you all for the attention and for finding a bit of time in your working day to join this hour. I hope it was worth your while. Thank you.
Thanks so much, Efren, for this really, really interesting talk. I'm trying to find a reaction button or something where we can give you a round of applause, but there doesn't seem to be any here. Yeah, at least from me, I'd like to appreciate my thanks for you taking the time to give this talk here. It's super interesting stuff. Also, I might add that in some ways, this is probably a bit more sort of acoustics and a bit less signal processing. And so I think for this technical area committee, this is super interesting in that it sort of brings in new knowledge into a society, because of course we can organize plenty of talks on familiar signal processing things. So I think this is a really interesting new information for our community. I should have said already when we started this that there's the opportunity to ask questions in the Q&A here. So yeah, my apologies for that. But if you have any questions for Efren, you can type away now, and I'll read them to Efren, and we can discuss a bit. Efren, maybe while people figure out if they have any questions, then maybe I can ask you here. So one thing I was wondering about is that these sound field reconstruction methods here, let's say the stuff that maybe is aimed at augmented, extended reality and that sort of stuff here. So what is the dimensionality of the involved problems, and how computationally complex is this? Is this stuff you do offline, or is it something we can see within 10 years? Maybe it's going to run in some VR headset kind of thing.
Yeah. And so I mean, this is offline, and I mean that's a really good question, especially so for the model that I presented, the part that's in time domain, it's quite expensive because of just because of the amount of samples that we're processing. And then it's especially that first study that was using solving or using Gaussian processes to solve it. Then it was the inference was huge, right? So then we had to resort to variational inference to to obtain an estimate, right? This is why also in the follow-up study that's currently ongoing, what we're going for is just the point estimate or the map estimate using regression just for that purpose. But it is it is, I think at least that first model, it would take still a while to run to run online.
Yeah.
But I should also say that the main motivation here was more to explore the potential benefit of having this how to say informative or quite structured model, to see how that would enhance the prediction ability, right? But of course, as it is now, real-time processing would be it's a bit far, I think. Still.
Mm-hmm.
Yeah.
But I personally like the philosophy of first trying to do it right, and then later trying to find
Do
the
it
trick way
quicker.
to run fast and all that.
Yeah.
Um, I suppose if you look at some of the sound field reconstruction methods, that some of the domains other than time domain that people do this in, it's done for two reasons, right? One is and maybe you can confirm, either to sort of facilitate manipulation in sort of some easy parametric way, or simply to reduce the computational complexity. Would you say so?
Yeah. And you mean doing it in frequency domain versus time? Or?
Yeah, or some modal domain or whatever.
Yeah, exactly. Yeah.
People.
And I know some of the work also from your lab on that. In our case, so we started looking at it in frequency domain, and what was happening there is that, especially if you have the different frequencies, slight reconstruction errors in phase and so on, then when you actually, especially the direct field, that's so important. When you actually go to time domain, there's a lot of artifacts due to the processing, right? So essentially what we were set out to do was to have a clear, well-defined direct sound, and it turned out that for that time domain was better. And then later in the later part of the reverberant field, because of random wave theory and the fact that it is so chaotic, then it didn't matter so much, and they're actually switching to frequency domain was certainly advantageous, right? So both in terms of the analytical models, they are just simpler, and also computationally, right? So, yeah. So that's where we ended up with that trade-off of starting in time and then switching to
okay.
Yeah.
Okay, thank you. Let me. Well, I have a ton of questions, but let me give other people an opportunity to ask some questions. So let me read some of the questions we received here. Okay. The first one is about the neural network-based approach you mentioned there with physically informed. The first question is, how is the wave equation actually encoded there?
Yeah, so it is through, I mean, as the problem is posed, so it's actually enforcing that the predictions of the network do follow the wave equation. In this case, the wave equation in time domain. So it's actually just modeled in the network directly, right? So yeah, so as you notice, there is a data fitting term, and then subject to the predicted field of the pressure, fulfilling the wave equation. And then once that is in place, then the prediction of velocity and intensity, it's just through auto differentiation. So in the forward pass, having the gradient, therefore you obtain the gradient over the space coordinates. In this case, it was 2D, so x and y, as well as the derivative with time, right? So yeah, so that's in essence, well, as far as I know how it enters.
Okay.
And then the second question is also really good, I think. So considering reactive intensity as a potential target for machine learning models. So what happens here is that because we are so the pin considers the wave equation in time domain, what we have is an estimate of the instantaneous time intensity, right? So therefore, and if you notice some of the figures, it was showing say forward going followed by negative going flows of energy, right? And then it's once you that is time average, then you obtain the real part, so active intensity, and then imaginary part, the reactive. So in the model that we have, because of being time domain, then we have both the active and reactive. The active shows us net energy that's flowing. The reactive part is the oscillatory, so basically back and forth intensity that appears there. So I think maybe I can just quickly go back to that slide. But for example, in this, let's see if it doesn't get stuck now, but I think you can see it, for instance, in this one, these converging waves, or so converging flows that you have here and diverging, those are going to turn out to being reactive. And indeed, as is pointed out in the question, this is essential or very important in enclosures because of the interference, right? So yeah, so it's great questions.
Okay.
And I hope that answers them.
Thank you, Efren. Let me read the next question so everybody can follow here. And this is a hopeful question from Anonymous. Will you be implementing this research into existing room acoustic simulation software?
Yeah, that's a good question. Yeah, so in fact, one of the things that we in this upcoming paper, let me just in this one that's coming this month in just one of the things that we did was in fact to use the pin for simulated sound fields in rooms. One thing of the pin is that it provides you a gridless mapping, right? So once a network is trained, then it is very quick to evaluate. And if you noticed, I'll go back to the architecture here. So if you notice here, the original features are space and time. So then you can actually once you have trained the model, you can actually just input any position of space. And then it will give you the predicted pressure, velocity, and intensity at that point, right? So it is a quite fast gridless mapping. So in that paper, what we included is a study where through simulated existing simulation software, provide a coarse map of a large area or a coarse points domain, and then use the network to interpolate that quickly, right? So yeah, so it's
Efren,
really
if I may ask, interrupt for a second here, because we actually have two questions which are about exactly this slide here, and the use of the sinusoidal function in the activation there, as the activation function there. Could you comment on that?
Yeah, so I mean, that's as I understand the what was done in this study, and I must say that the work here. So Xenophon was working on different implementations of the network, and simply when using sinusoidal activation, the results were much better. Yeah. Also, at first, when we started on this, we didn't have these two encoders. So directly the features of space-time were going into the MLP, and then just trying these changes, this turned out to be the best the best model, right? So that's as far as I can comment that when using the sinusoidal function, then the predictions had significantly improved. Yeah.
I see. Okay. Then there's a question about the ground truth data, which is what level of accuracy do you expect in the ground truth data in the slide about the Royal Theatre?
Yeah. So I mean, I think that I think that what we measured is, it's as true as it gets. I must say that what happened there is that because of the long impulse responses, like we just, like when you consider the length of the sweeps compared to the length of the impulse responses, these measurements are more noisy than the ones that we did in the room, and also because we had these time limitations. So because of the show in the evening. So I think that in terms of the spatial accuracy, it is fairly accurate in terms of the waves that we are seeing. Now, the impulse responses are certainly noisier, And then when you think of how that noise propagates in the prediction of velocity and intensity and so on, then for sure there's some noise that we are observing there. Yeah. So. Yeah.
Okay. Maybe we have.
And I'm happy to see some familiar names here in the question. So greetings to everyone that showed up.
Let's see. Any more questions from the audience? It doesn't seem like it, but in that case, Efren, thank you so much for your talk here today, and
thank you very much.
I know you've been on parental leave and all.
Yeah.
Yeah. So thanks so much for taking the time.
Yeah. I took a leave from the leave, so now
yeah. Well, we appreciate that very much,
to...
Efren, and we hope that maybe in the future we will also see you at EURASIP events.
Yeah, I'll be very happy to join, and thank you again for the invitation, and it's a pleasure.
It's our pleasure, Efren. Thanks so much, and thanks everybody for the support. We hope to organize more of these types of events. I think it's a great way of learning new stuff. And I also want to say that should you, the attendees here today, have ideas for future webinars, they're free to send me an email. Thanks so much, everybody, and thanks to Efren once again for the talk. Bye-bye.